Implementation of Reed-Solomon codes for stratospheric balloon probes and nano-satellites. Abstract. The digital communications and data handling techniques are essential in any system that require to store and transmit information from one point to another, and if the system has to work remotely, the software, as much as the hardware, is a key part when it comes to compensate errors in the data due to the environments with high electromagnetic noise, fluctuating power source or a changing visibility window to transmit. Usually, the purchase of a communication system with a sophisticated built-in error correction codes, ECC, are quite expensive and, depending the country, always there is security restrictions. Therefore, in order to increase the performance of scientific data gathered from stratospheric balloon probes and nano-satellites using entirely low-cost commercial components, we develop a communication system to transmit/receive data files above 5 kb with low-cost commercial RF transceivers, commercial ARM-based mini-PC and using an implementation of Reed-Solomon codes. Keywords: TX, RX, Reed-Solomon codes, error-correcting codes, components off-the-shelf, ARM-based, Galois field, codec. 1. Introduction. The use of components off-the-shelf or COTS-based solutions has allowed to develop radio probes, payloads, and many satellites with modern tools and a minimal cost that a couple decades ago, by getting full advantage of the economy of scale with cheap and plentiful components. Due to the typically shorter lifespan of these devices compared to traditional endeavors, it is possible to use newer, more innovative designs without running a high financial risk. This is interesting as it allows for rapid development and advancement in an otherwise conservative industry where only the large companies and agencies could afford such developments. 1-2. However, in order to increase the reliability of the COTS-based devices, it is necessary to make thoroughly analysis of the environment conditions where the devices are going to operate and to replicate such conditions. Then, identify the weak points where the device shows poor performance or a risk of failure, so the development team can improve/replace/optimize such features. 3. When it comes down to data gathering, the performance improvement of the digital communication system is possible. One way to do this is to increase in the signal-to-noise ratio, SNR, by increasing the transmission power or by changing the antenna gain but usually the transceivers with high transmit power are expensive, without mention the transmit permits, depending of the country, required to do so. Also, the physical size restrictions of the nano-satellites and balloon probes makes unfeasible the increase of the power source. 5. The other method is the implementation of a forward error correction, FEC, that is a type of ECC that does not require handshaking between the source and the destination. It is less costly than these techniques. Introducing channel coding in a communication system introduces the possibility of approaching the maximum transmission rate theoretically possible for. The FEC method is favorable because have a lower consumption of bandwidth and a high efficiency error correction. This is the reason FEC is suitable for applications in wireless communication. 6. Hence the Reed-Solomon codes are chosen. The proposed solution is to have a RS codec implemented in our communication system. The data is compressed in certain format, depending of the type of file, divided in smaller packages, encoded and transmitted through a RF transceiver. From the other side, the receiver control software gather the packages, decode them and detect any erroneous byte and determine their exact location inside the package in order to intend to correct them. To test that the algorithm does work, we make 2 tests. Burst of errors, by passing the data packages through a random number polynomial generator. In this test we determine the number of errors inserted. Random errors, by adding an additive white Gaussian noise, AWGN, array, to the data package. The probability of error is independent from one transmitting byte to the next. For the moment we are not conducting any further tests concerning to the RF signal or the transceivers. Where the RS codes may be shortened by conceptua. Reed-Solomon codes. The Reed-Solomon, RS, codes are a subset of BCH codes, Bose-Chaudhuri-Hoekwengham codes, that is a class of cyclic error-correcting codes that are constructed using polynomials over a Galois field 8, 9, 10. With a wide range of applications in digital communications and storage, Reed-Solomon codes are able to detect and correct multiple symbol errors. 7. A Reed-Solomon code is specified as, with m-bit symbols 14. This means that the encoder takes data symbols of bits each and adds parity symbols to make an symbol code word. There are parity symbols of bits each, Fig. 3. A Reed-Solomon decoder can correct up to symbols that contain errors in a code word, where 2 equals. In our software, we already know that this 0 bytes are not important, so we adapt the calculations so we can ignore these added 0 bytes and save computing resources. We define the package size to encode/decode equals 128. The proposed the number of bytes of parity and hence the max number of error detection per package. 2 equals 32. Number of bytes then can be corrected per package of equals 16. When a target file is requested to the onboard computer, the data array is divided into small pieces of 128 bytes, then it is encoded and concatenated with its respective parity bytes and then sent. For the purpose of this paper, we are only going to describe briefly the mathematic procedure followed to implement the RS codes without taking into details. Finite, Galois, field. Reed-Solomon codes are based on a specialist area of mathematics known as Galois fields algebra. A Galois field or finite field is a set of elements in which we can do addition, subtraction, multiplication, and division without leaving the set. The operation of addition and multiplication must satisfy the commutative, associative, and distributive laws. The generator polynomial. A RS code word is generated using this polynomial. It is defined by the size of the parity bytes and composed of the minimal polynomial of the 2. It is used for the encoding and decoding the message 12. Once the size of the parity bytes, 2, is chosen, that is powers of 2, it is proceeded to compute all their minimal polynomials in order to produce the generator polynomial. 4. Using Galois algebra for a binary field we obtain our generator polynomial, EQ10. In the figure 4, it is shown the results of our generator polynomial function in the communication software. 4. Calculate the decoded code word from the received word. Syndrome calculations. Every code word is created so that it can be divided by the generator polynomial. Therefore, if we evaluate a word in any of the roots of, we will obtain 0, no errors, as result only if it is a code word. A RS code word has 2 syndromes that depend only on errors, not on the transmitted code word. We can get the syndromes by evaluating the word in the roots of the generator polynomial, are the roots of the generator. The ITH syndrome is defined as. We define the received data as, and is the sum of the original code word, plus the errors/erasures. The decoding process takes a quite large process that the RS encoding. Calculate the syndrome components from the received word. Calculate the error locator word from the syndrome components. If every syndrome is 0, then we can be sure that the code word has no errors. By the other hand, if just a syndrome is different from 0, the code word does not have one of the roots, therefore it cannot be divided by. If that case happens, it is necessary to detect the errors. To solve such system, there are several algorithms to do so. The most popular are the Berlekamp-Massey algorithm 1011 and the Peterson-Gorenstein-Zierler algorithm 15, and to find the roots, x, of the error locator polynomial it can be used the Chien-search algorithm 16. Error correction. Once the error locations are known, the next step is to try to estimate the original value of. This can be achieved by using the Forney algorithm 1113. The error values are then used to correct the received values at those locations to recover the original code word. Performance metrics of digital communications. We can almost say for sure that the main goal of the digital communications systems is the accurate transfer of data bits as fast as possible. 19. The primary measure we are going to use to evaluate the RS performance is the bit error rate or BER. The BER can be defined as the estimated probability of bit errors. In practical testing, it is measured by transferring a finite number of bits through the system and count the incorrectly received bits by comparing with the original data, EQ 25:20. Necessary to send every package and wait an interval of time, depending of the transceiver model, to finish the sending to 18. Corrupting it. The image is a picture of the large millimeter telescope Alfonso Serrano located at the Valca and Sierra Negra. As mentioned before, during the transmission, the package passes through an error burst generator block, Fig 8, where a certain random number function generates a burst of errors to be inserted in the data. The quantity of errors is determined by us manually during every test. For the AWGN test, the block generates a white noise signal array where we only determine the standard deviation and the mean of the signal noise, so it is expected then the number of errors be above of 2 tons in some cases, meaning that some images will not be fully recovered. Experimental results. The algorithm has been able to receive the image data, decode every package and concatenate it to restore the original file as it is shown in the table 3. As a comparison, it is also shown the image file as it would be before the RS decoding. The AWGN test results are shown in the table 4 and 5, where it is observed then, since we cannot set the quantity of errors to be below 2 tons, the file is partially recovered but legible. To measure the performance of the data transmission, we calculate the BER before and then after the RS decoding. This is achieved by comparing the original data sent, before adding the AWGN, with the data decoded in the receiver control program, Table 4. This process was done several times using different image data sizes. Conclusions. We have been able to implement a working RS codec that can be used in ARM-based OBC as well as ported to Windows OS. We tested their performance using entirely low-cost COTS transceivers and determined that it is capable to find and correct errors in data files of different sizes. To improve the performance of the RS codec, it is required further analysis of the time execution.